Okay, so last time we talked about, so we had a function or sequence of function. We had an interval, say I, and we had a sequence of function fn and a function f, all defined on this interval. And then we talked about pointwise convergence. So pointwise convergence meant that for each, so this is for each x, when you're looking at this, so this is for each x fixed, this is a sequence, this is supposed to converge to f of x. So this was pointwise convergence, and then we also talked about uniform convergence. And this meant that for all epsilon greater than 0, there exists a capital N, such that if little n is bigger or equal to this capital N, then the difference between fn of x and f of x, this here is smaller than epsilon, and this here have to hold for all n, for all x, sorry. Right, so uniform, again, refer to that is uniform in x. The convergence is uniform in x. Then, so we talked about that. And then one of the theorems we proved was that if you take a sequence, fn and these here was integrable, and these converge to some function f, then f is integrable. So this here is uniform convergence. Then f here is integrable, and the integral is the limit of the integrals. So the integral from a to b of fn x dx is the limit here of this. So the limit exists, and it is equal to the integral of f. Okay. Now, so this is how uniform convergence and integrals interact. If we take suppose you take a sequence here, so this is a theorem, that suppose you take a sequence fn of functions on some interval into R. You have x0 is in this interval. And then you have the following, if you have the following properties, that one is that this sequence here converge to some number c. Sorry, the sequence here converge to some number c. 2 is that these functions here, fn, are differentiable. So these are, maybe I'll just say here, that they're differentiable. And these here converge to some function g. And then 3 is that these functions here, sorry, the derivative converge. And I'm also requiring that the derivative are continuous. Suppose we have these 3 things. So we have the sequence of differentiable functions. If you just fix this one particular point x0, then the values of these functions converge, and then the functions, their derivatives are continuous, and the derivative converges to some function. And this convergence here is uniform. Then the claim is that then then there exists f on the interval, so that f is differentiable. The derivative here is continuous, and you have the following two properties: that the function here, these functions converge to f uniformly. I'm going to restrict my interval. I'm going to take it just to be some interval from a to b. Sorry. And this is the interval. I want it to be bounded. Like that. And so these here converge uniformly, and true is that their derivative converges to the derivative of f uniformly. Okay. So we want to prove that, and then so we're going to define a function f. So g here is a proof of this, since this sequence here, since these here are continuous, and these functions here converge to g uniformly, then this means that therefore g here is also continuous. Right? So we proved this already, that if you have a sequence of continuous functions that converge uniformly, then the limit is also continuous. And so then we can look at, so we can therefore define f as a function on this interval here by that f of x is equal to the integral from x0. So I'm defining it, to be the c, constant c, plus the integral from x0 to x of g of s ds. Right, so I define this function like this. G is continuous, so this is a nice continuous function, and in fact, by the fundamental theorem of calculus, f here is differentiable with the derivative equal to g. Right? We also have that that if we're looking at f of x0, fn of x0, right, then we know already that these converge to c. This is the assumption 1 up there. But this here is the value of f at x0. So we have that. I want to now prove that not just at this point, but but that this sequence converts to F uniformly, right? B here, B we get for free, right? So B follows from that this Fn prime converts to G, right? And this here is the derivative of F, and we have this uniformly by assumption 2, right? So all we need to show is, so we just need to show that this Fn converts to F uniformly. Right, we just need to show the the property A, right? And so we're looking at Fn of x. We have to look at this difference, right? And for a given epsilon, we have to find a little n. So we have to find a capital N, so that if little n is bigger than this capital N, then this difference here is smaller than epsilon for all x. Right? But let's try to estimate this here first. Right? So this difference here is f. Right, so we can write. So we want to estimate this difference, and we can use the fundamental theorem of calculus. So use the fundamental theorem of calculus. To write Fn of x. We can write this as the value at x0 plus the integral of the derivative from this point. And then this here should be an s, like this, right? We can use the fundamental theorem calculus to just rewrite Fn like that. And so now I want to look at this difference here, right? And so to look at this difference, Fn of x minus f of x, now I can fill in this form of it. So I have that this is Fn of x0 plus the integral from x0 to x Fn prime s ds. And then I have to subtract f of x, but f of x was given by this formula here. And so minus c plus this integral here. G of s ds, like that. And so now I'm just rearranging terms. So I just think about this thing here as Fn of x0 minus c. I take these two first, and then plus the integral of x0 to x f prime n s ds minus this integral here. Like that. Right? And then I use the triangle inequality, that this thing here is less than Fn of x minus c, Fn of x0 minus c, absolute value like this. And then I have the second integral here. So the absolute value, or the difference here, if you do it slowly like this, so you have this minus this thing here, of g of s ds, like that. Now I can think about this thing here as I can find the integral, so I can write this thing here as, so this I'm just keeping, this first term here I'm just keeping. And then the second here, I can think about this as an integral of the difference of these functions. And this here was an n here. Like that, right? And now, now I can so now I can, here I can just take the absolute value sign. If I take the value sign in under it, then I get something potentially larger, right? So this thing here is less or equal to fn of x0 minus c. That's the first term. And now I'm replacing it by something that is bigger or equal to this. So where I'm just integrating from x0 to x, and then of this difference here, fn prime s minus g of s ds. And now I'm using that the fn. So now using, so since fn of right, so right. So let me just write this thing here. So I can write this thing here. This one here I'm keeping. This one here I'm keeping. So I'm writing this as less or equal to keeping the first term. And the second term, you see, this thing here is this difference between these two. Well, the difference is at some s is smaller than the maximum for all s, right? But the maximum for all s, that's what we call d fn prime g, right? That was the maximum over all s. And so now we just have, so this function in here is less than this. And now we are using, this is where I want to use that the interval is bounded. So I just get plus b minus a. This is the length of the interval, like that. Right? And so now you see that as, and now there's no reference to x on this side, right? And so you see that as n goes to infinity, well, this thing here goes to 0, and this thing here goes to 0. Right? So as this goes, this upper bound goes to 0. And again, note that there's no reference to x. There's a reference to x0, but that's just some fixed point, right? So this is uniform in x, right? So this implies uniform in x converges. Okay, and so I want to draw some consequences of this. First, let me look at what will be shortly a particular case of a more general phenomenon. So this is this example we looked at several times last time. So, but it's now applied in this case here. So suppose you're looking at the functions en of x. The en is where you're summing from k equal to 0 to n of x to the power k divided by k factorial. I looked at those last time, these functions, and we called them en. And then we also looked at the exponential function. And the exponential function, in terms of power series, that was just this power series. Right? And we have that that En here, so that for all this we used Weierstrass M-test so by Weierstrass M-test for all L so positive real number, we had that these functions converge to E uniformly on an interval like this. They don't necessarily, in fact, they don't, but they, you know, the claim here about uniform convergence is just on every bounded interval, right? So you fix a bounded interval like that interval, and then you have uniform convergence. It's not like uniform convergence of all of R at the same time. Okay, so we have that. And now, if we are looking at, so now, if we're looking at the function, if we take now the derivative of the ENs, so what is the derivative of the ENs? So the derivative of the En, right, the En is just a polynomial, so you can just differentiate each term on its own. So this here is the sum here of k x to the power k minus 1 divided by k factorial. And here you would be summing from k equal to 0 to n, right? This is just the right. And now I can write this also. You see, the first term, because when k is equal to 0, the first term doesn't really count, right? So this thing here I can write as, I mean, it doesn't count because it's 0, right? So you don't really need to write that term. So you can just write it from k equal to 1 to n, and then you can write it again as k times x to the power k minus 1 over k factorial. But k factorial is just, it's the same as k times k minus 1 factorial, right? So this means that k factorial over k is just the same as k minus 1 factorial, right? Or if you will, if I take the inverse of this, k over k factorial is the same as 1 over k minus 1 factorial. It's just flipping the numerator and denominator. So this finite sum I can write as k equal to 1 to n, because you see this thing here is exactly this, so we can just replace it. You can write it like that. But now, this thing here, I'm summing from 1 to n. The first term I get, that is just this here, by definition, when k is equal to 1. That's 0 factorial, by definition is 1. Right, so this thing here and this thing here, by definition, is also 1. So this here is just 1. So starting off at 1, when k is equal to 2, then this here become x. This here become 1 factorial. 1 factorial is just 1. So this here is x, right? So this here is like this, x. The next one, when k is equal to 3, then you get x squared. You get x squared. and down here you get 2 factorial, right? And so you continue like this, and the last one you get is x to the power n minus 1 over n minus 1 factorial, right? And so, yeah, let me just say, so you see that this thing here is nothing but e n minus 1 of x, right? So the derivative of the en is the previous element, en minus 1. Yep. Okay. Okay. So now we have that these en, if I'm looking at the en is 0, the value here of these guys, the only term that matters is the first term, and that's 1. So this here for each n. So now what you have is, so now we have that if you're looking at this sequence, we have this, we have that the en prime is equal to en minus 1. And we already proved that these here, it doesn't matter whether you're looking at the previous one, that they converge to E uniformly, right? This is a uniform convergence. On this interval here. And then obviously the en prime here, their polynomial, so continuous. Right. So now we have that. Therefore, by the theorem, there exists some function f so that these here converge to this uniformly. That's no great surprise. And we also have that this thing here, the derivative converges to the derivative of this here uniformly. And again, this is on intervals of this form. Right? Well, we already know that it converges uniformly, right? This is just it can only converge to one function, right? Because uniform convergence means that it's converging pointwise at each x, and pointwise convergence, then the limit is just one thing. So we already know that this here is E of x. So you see that the conclusion here we get is now that this here, is, as we said, en minus 1. So the conclusion that we get is that the E, so this is the conclusion from the theorem up there, that these en minus 1 converge uniformly to the derivative of this function. Right? Right, the theorem said that if you have these three conditions, then there exists a function f so that is differentiable and the derivative of it is continuous, and you have these two properties. But we already know that these converge to this. So we've already identified what this function is. So the theorem just gives us that this function must be differentiable and the derivative continuous. And now we try to figure out what that derivative is. But the derivative of these functions are the same functions we started with, but just shifted one backwards, right? So these here, also they converge to this. That's what the theorem say. But the en minus 1, they also converge to e, right? So this means that these two functions here, this here, and this here, must be the same, right? So this means that e is differentiable, and the derivative is itself. Yeah.
So we define this for like all n greater than some.
This here was for all. This here was defined for any non-negative integer.
Okay.
Right, and so, I mean, when I'm talking about it down here, then I'm saying about n bigger or equal to 1, because I didn't strictly speak define e minus 1. Right? Okay. So now I want to sort of do this more generally. So I take a power series. Also, by the way, the plan, so after this lecture, there's 2 more lectures, Thursday and Tuesday next week. And my plan is, I already updated, the course plan to reflect this. So my plan is like next time I will prove existence of uniqueness of some ODE, using things we have learned here, about metric spaces. And then Tuesday next week, we'll do a review of the class. So there won't be any new material on Tuesday. Okay. Also, for whatever it's worth, I decided in the end with a friend to turn in the lecture notes, to turn it into a book, just because the TBB, that was like the main reference, I didn't find that great. Anyway, it was also, at 1,000 pages, who want to read 1,000 pages, right? So, so the course note here is like shorter, as you probably have seen, and trying to focus on the the key points. Okay, so eventually there will be a book. Okay, so now. So now, So now I want to do this sort of more generally. So we take a power series. So we have AN as a sequence, and we're looking at a power series like this. So this here is a power series. And so just to remind you, the radius of convergence is given as follows. So we take M, and M is defined to be the lim sup as n go to infinity of the n-th of absolute value of AN. Right? And then the radius of convergence, so R here is then 1 over M, with this usual convention that if m is infinity, this here is 0. If m is 0, this here is infinity. Right? And so then we have, again, that we have that, so we have that the series here. So if you're looking at this k equal to 0 up to n of an xn, this here converts to this limit here uniformly on each interval of this form here, where L here is strictly less than 1. Okay? And this is again, this here is Weierstrass M-test. Now, what I'm interested in is, so I want to be able to calculate the derivative of this. So we define a function f by that f of x is equal to the sum here from k equal to 0 to infinity. So this is the power series x to k, like that. And we want to want a formula for the derivative, and in fact I want a formula for any derivative of so say the mth derivative of this function. And so right, so now I look at, so we had take this power series, and I'm looking at the power series that is given by, right, so if I take, so it's supposed to be looking at the power series where for each term, so you have in the original power series, it's an times x to the n. Then I'm looking at n times x minus 1, like this. Right? So, and here I'm summing from 1. I mean, it doesn't matter. I can sum from 0. So 0 to infinity, like that. Now the radius of convergence for this, so what is the radius of convergence? So of convergence. The radius of convergence for this is the nth root of n times a to the n, like this. And this thing here is the same as n to the power 1 over n times the nth root of an, like this, right? Now, this thing here, if you're looking at n like this here is, you can write this thing here as e, and then it's log n over n. This here, as n goes to infinity, converts to 0. So this thing here converts to 1, right? E to the 1. And so you have that Lim sup here. So the Lim sup of the nth root of n times an, like this. This thing here is, because this here, right, you can write this, it's the same as Lim sup. So n go to infinity, so n go to infinity. It's the same as the n root of this thing here times the n root of like this. This here converts to 1, so it really just converts, so it's equal to the lim sub as n go to infinity of the nth root of an, right? So, and that was what we called m originally. So this lim sub is the same as this lim sub. So this means that m for this new sequence is the same as m for the old sequence. So this means that the radius convergence for the new sequence is equal to the radius of convergence from the old sequence. Right? So if you take the derivative term by term and you form this new power series, then it has the same radius of convergence as the original power series. Okay, and so now you can iterate this. So you can iterate this. So you can take the, so this is just taking the derivative term by term one time. If you now take the derivative, suppose you're starting with this sequence here. So you're starting with this power series, and you're taking the derivative term by term. Then you get, as we did up there, you're getting this power series. Sorry. Now you take a derivative again, term by term. So you're getting this, right? And the thing is that each time the radius of convergence for this, same radius of convergence, these two here, same radius of convergence, right? It's because of the same principle, same radius. And so on. And so you can continue. And if you do this, m time, then you're getting n. Then so right. So if you do this m times, then you get that this thing here is x minus m, and you're getting an, and here you're getting n minus 1, n minus 2, up to n minus m plus 1. Right? This would give you, so you're getting that, right? So that is after. This is when you do it m times. And so, again, these here will have the same radius of convergence, right? Now, yep. Now this thing here, right, so what is, so n, if I want to write this a little bit more compactly, so I'm thinking about this thing here, n minus 2, up to n minus m plus 1. I can write this thing here as n factorial, and then, but then I'm getting all these, so if I wrote it as n factorial, then I would also have, right, it would keep going like this, and the next one here would be n minus m. Right, so if I'm writing, so I can write this thing here times this factorial is equal to that, right? Yeah, sorry. Right. So I think you were complaining about one thing that I sort of pushed under the rug, and that is the following: that if you if you take the way we defined, so if you take a power series, again like this, and you define the radius of convergence, then you define it from this n element, right? I think that's what you're complaining about. And so you take the coefficient to the n power. That's not exactly what I did. Is that what you're complaining about? Yeah. And that doesn't matter, right? And the thing is that, so when you define the radius of convergence, you took this n power like this, right? But this was to this, there was coefficient to where this here was to the n. When I'm doing it over here, there's two ways of dealing with it. One is the one you suggest, and the other one, and that was why I put it under, I stripped it under the rock, is that the way the radius, this with the radius convergence, it comes from comparing it with a geometric series. And then it really doesn't matter for this term in terms of x, whether you have shifted it or not, okay? But if you do it as you are suggesting, which would be totally fine, then let's see, so then this thing here, what you really should have done is that we should have thought about this n, an, and then we should take this here, and we should take, instead of the n root, we should take the n minus 1 root, right? But that doesn't matter either, right? That's going to be the same also. Yeah. So either way, you can check either of these two things. And I was thinking about the first, and where it's coming from, right? Okay, so now, right, so sorry, now I lost my thread here. So I was just observing that if you can write the n factorial as first taking all of these factors and then taking n minus 1, right? So this means that n factorial divided by n minus 1, sorry, n minus m factorial. This is equal to n minus 1, n minus 2, down to n minus m plus 1, like that. Right? But you see, that's exactly what we have done here. Right? So this thing here, so what I conclude from this is that if I take a power series, if I take a power series like this, and I take the derivative term by term, then, and I do this m times, then this is what I get is n factorial n minus m factorial, and then a n x m n minus m. Right?